Hello guys, this is Prime Concept. In this video, we want to consider refraction at the plane surface. In our previous videos, we looked at reflection, which had to do with mirrors. We considered the plane mirror, we considered the curved mirrors. Now in this video, we want to consider the concept of refraction at a plane surface, after which we can now look at refraction at curved surfaces. So try to get the difference. This is the term refraction. Now, when you have a plane surface, you have a smooth surface, which this board can represent. If you flash light, if you have a plane surface that is, let's say, transparent, and this board is not transparent, so we cannot really use it. Now we have a plane surface that is transparent. If you flash light on that plane surface that is transparent, you would notice that when the light comes out from the other side, that the light will bend, right? So that phenomenon is what we want to consider in this case. Now, what is the term refraction? Refraction simply means the bending of light rays as it crosses the boundary between two different media. That is refraction. Let me repeat. Refraction means the bending of light rays or the bending of light as it crosses a boundary that separates two media. Now, what do we mean by that? If I have this as a plane and a smooth surface, so this is a boundary. This line would represent a boundary between this medium, say medium 1, and then we'll have another medium 2. So we have two media here. So when light is traveling from this part and entering this part, there would be, it would expected, or it would expect it to bend, right? So that phenomenon of which light bends when it crosses a boundary that separates two medium, that phenomenon is what we know as refraction. And the only case where when you incident light from one medium to another, it does not bend, is when that light is incident at right angle to the surface. So in that case, the light will travel straight on undeviated. It won't bend, right? So that is the idea of refraction, bending of light. Say I have a perpendicular line like this, which represents what you know as your normal. If I incident light in this first medium, if I incident light such that the angle of incident is I, when this light enters this other medium, it will bend either away from your normal or towards your normal. So we would have this. So this line you can see here now, this ray is what we call refracted ray. So this is known as refracted ray, while this one is known as incident ray. Incident ray. So the angle that the refracted ray makes with your normal, this angle is known as angle of refraction. We denote it with small letter r, right? So don't mix it with reflection. So this is angle of refraction. So you would notice that this light, this ray is already bending from your incident ray, because the incident ray normally should go in this straight form, but because it is now bending, so this bending away from the normal direction is what we know as refraction. Now we can have two conditions. So we can have a condition where our refracted ray would bend towards our normal, would come close to our normal. We can have another condition where our refracted ray would shift or move away from our normal. So the behavior would depend on the nature of the medium or the media you are dealing with. So I want to state those two conditions very quickly so that you note them. Now, the first condition occurs when light moves. When light travels from a less dense from a less dense medium to a denser medium, comma, the light moves towards the normal. So I'm just taking my time to write this so that you can take note of it and see it as a very important point. So this is the first condition. When light travels from a less dense medium into a denser medium, the light ray will tend to move towards the normal. So this is what you would have in first condition. So if this is your incident ray, this is the angle of incidence. When it travels, you notice that your refracted ray will move towards your normal. So in this case, your angle of incidence, in this case, your I is always going to be greater than your R under this condition. And you should take note that this medium is denser, this one is less dense. So when light travels from a this is less dense, this is denser medium. So when light travels from a less dense medium to a denser medium, the refracted ray tends to move towards your normal. What is an example of this pair of medium and media? An example of this is when light is traveling from air to water. If this first medium is air, so this is air and this is water. So this is going to be a good example of less dense to denser because water is denser than air. So when you have this scenario, the refracted ray will bend towards your normal so that your angle of incidence at all points, at all time, would always be greater than your angle of refraction. Now, if we have this particular scenario, now of course, you know that assuming there was no refraction, you would expect that your incident ray should travel straight in this direction. So, but because there is refraction, so it is now deviating from the normal direction. So in that case, the angle by which the incident ray deviates from the normal direction is what you know as angle of deviation. So this angle here is called angle of deviation and usually denoted by the symbol delta, small letter delta, or some books use D, small letter d. So this is known as angle of deviation. So what is the relationship for angle of deviation under less dense to denser medium? How do you find your angle of deviation? It's very simple. You'd use the concept in mass that says that this whole angle is going to be equal to this whole angle. And what is the reason? They are vertically opposite angles. So if we do that, it means that delta plus r in this case should be equal to the whole angle here, which is I. Then so that delta becomes I minus r. So this particular equation you can use to find the angle of deviation, right? And this equation again will tell you that your angle of incidence would always be bigger than your angle of what? Refraction. And that is why you can take away your angle of refraction from your incidence. Now let's look at the second condition. Condition 2. So the second condition is when light travels from a denser medium to a less dense medium. So when light travels from a denser medium to a less dense medium, the refracted ray tends to move away from the normal. So this is what we have in this case. So this is our dense or denser medium. This is our less dense medium. So our less dense medium, right? Now, if you have this is your angle of incidence. When it enters this, your refracted ray will tend to move away from the normal. So these are refracted ray, and you can see the angle of refraction. So you can see how big the angle of refraction is. So this simply tells you that under this condition, when light travels from a denser medium to a less dense medium, you will always have that your angle of incidence would always be less than your angle of refraction. So this condition, and this is true for this condition. Now, if you check again, if this incident ray is allowed to travel straight, you would have something like this. This would be the path it should go. But because it does not travel straight, it refracts, it bends, right? So the amount of angle by which it bends away from your normal direction is what we know as the deviation, which is delta in this case, right? Now, how do we find the amount of deviation in this case? It's still very simple. Now, if you look at this, you still use the principle we used in the first case. You'll still see that this angle, this part, is also vertically opposite to this. So this, anything you have here should be equal to I. So how do we get this angle? Very simple. You know that the total angle is R, and then only this part is delta. It means that this part, this small part, is going to be what? You are correct. It's going to be R minus delta. That is this small part. R minus delta, this small part. So this part is vertically opposite to this, so they are equal. So I'm going to equate this to what now? To I. So if I do this, I want to find delta. So I'll quickly bring I to this side and take delta to that side. So I'll have R minus I. When delta minus delta crosses, it becomes plus delta. So that we can just say that delta is R minus I. So this is the relationship for this condition. And very quickly you would see that R is again greater than I. And that is the reason why you can take away I from R. So under this condition, your angle of incidence would always be less than your angle of what? Refraction. What is the condition? When light travels from a denser medium to a less dense medium, which you can still call rare medium. I believe this is very clear to you. And the next thing we want to consider in this case is the laws of refraction. The laws of refraction. So there are two laws of refraction, or there are two laws known as the laws of refraction. So the first, I will be stating the first law. First law simply says, it's similar to what we did in reflection. So the first law of refraction, or one of the laws of refraction, simply says that the incident ray, the refracted ray, and the normal at the point of incident lie on the same surface. The incident ray, the refracted ray, and the normal at the point of incidence lie on the same surface or plane. So I explained that when we talked about this similar law in reflection. So a plane simply means a surface. So we are just saying that those three rays are on the same surface. So you won't have one on this part and then you have another one on this part. So the three of them are on the same what? Surface. So that is what that first law is saying. The incident ray, the refracted ray, and the normal at the point of incidence lie on the same plane. So this is what the law is saying. Now our second law Our second law of refraction is very simple. Our second law of refraction is also what we know as Snell's law. Snell's law, which virtually all students are familiar with. So the second law is what we know as Snell's law of refraction. Now, what does this second law say? The second law simply says that the ratio of the sine of angle of incident to the angle of refraction for a given pair of media is constant. The ratio of the sine of angle of incident to the angle of refraction for a given pair of media is what? Constant. That is what the law is saying. And what is this constant we're talking about? The constant is what we know as what? Refractive index. So in a mathematical form, we can write Snell's law in a mathematical way. We can represent Snell's law by saying that the ratio of the sine of angle of incident to that of the angle of refraction for a given pair of media. So when you have two media, so for a given pair of media is equal to a constant. So it's equal to a constant, and that constant is what we know as what? Refractive index. So what it means is that we can say that sine I over sine R is equal to n. So what is n? Where n is known as refractive index. N is called refractive index. Refractive index is just a number. So it's a number that tells us how light travels from one medium. So it's a function, it's a constant that actually depends on the speed of light. So it tells you how the speed of light changes as it crosses from one medium to another medium. That is what refractive index tells us, right? Now, one thing that students really need to understand is refractive index. So a lot of students don't really know the idea or what is embedded in refractive index. Now, what we have written, n, refractive index in this case, is what we know as relative refractive index. So that will bring me to the next point I want to explain about refractive index. So do well to take notes while you're watching me. This would really make this concept very easy for you. Thank you. Now, I want to quickly talk about refractive index. And so we have two types of refractive index we always consider. So there are two types of refractive index. Of course, they are still saying the same thing. So the type of refractive index we have, number one, is what we know as absolute refractive index. So which will just denote by n without any subscript attached to it. So this is absolute refractive index. I will denote it anyway with n. Now, number two, we have relative refractive index, right? Which some books denote with this. Some books still use n, right? And then they attach numbers to it. So absolute and relative. Now, what is the difference between these two refractive index? The absolute refractive index is the actual refractive index of a medium. That's the absolute refractive index, the actual refractive index of a medium. For example, the absolute refractive index of air is what? You are very correct. The absolute refractive index of air is 1. Next, the absolute refractive index of water is what? Is 1.33. The absolute refractive index of glass, right? The glass that is commonly used for our prism. Say we have this. This is my prism. Yes. So the absolute refractive index of prism, of glass, this kind of glass, is what? Is 1.5. So these are what we know. These are what we know as absolute refractive index, the actual refractive index of that given medium. Now, what is relative refractive index? Relative refractive index is the refractive index of one medium with respect to another medium. It is the refractive index of one medium with respect to another medium. So what we have seen in Snell's law is actually the relative refractive index, right? So if we have a situation like this, if we have this is I, so this is medium 1 with refractive index N1, and then we have this is R, this is medium 2 with refractive index N2. So what it actually means, according to Snell's law, since if we are considering less dense to dense, what Snell's law actually means is that the ratio sine I to sine R is actually going to be N2 over N1. So this is what Snell's law is actually saying. And what is N2 over N1? N2 over N1 is usually denoted by this mu from medium 1 to 2. This is usually denoted as this. So this is actually N2 over N1. So this is actually what Snell's law is saying, which, for the sake of simplicity, which is actually preferred by me, you can simply interpret Snell's law like this. You can simply interpret this. If we cross multiply in this equation, if you cross multiply, then you would have that N1 sine I would be equal to what now? N2 sine R. So we can simply interpret Snell's law like this, where N1 is the refractive index of the first medium, then sine I, right, incident angle, then N2 is the refractive index of the second medium. So this, I believe, is very clear to you. Now, so you should note from what I've explained so far that we have two types of refractive index. N1, N2 in this case is absolute refractive index of the second medium. N1 is absolute refractive index. So the ratio of absolute refractive index is what you know as relative refractive index. So while this is relative refractive index, each of these is absolute. This is absolute, while their ratio is a relative refractive index. So let me give a simple question to illustrate this. Now, if light travels from medium 1 less dense to medium 2 denser, of course. Now, if the refractive index N1 in this case is 1 and the refractive index N2 in this case is, say, 1.5. So, and I want you to find the refractive index. I want you to find the relative refractive index of glass. The relative refractive index of glass. So what is it going to be in this case? The relative refractive index, say this is your glass, because you know that it is glass that has 1.5. So this is glass. So the relative refractive index, which is going to be the refractive index from medium 1 to the refractive index of medium 2, the relative refractive index of glass is going to be what now? 1.5 as medium 2, or let's put it this way, it's going to be N2 divided by N1. So the relative is always that of the second medium, which is the denser, to that of the first medium, the less dense. So we're going to have 1.5 divided by 1. So in this case, what do they have? We have 1.5. So this is the relative refractive index. So if you are trying to find the relative refractive index of any medium with respect to air, it means that it would always have the same value as the absolute refractive index. So N2 is the absolute refractive index of glass, which is still the same value as the relative refractive index with respect to air, because the refractive index of air is 1. So when you're trying to get relative refractive index with respect to air, it would always be the same as the absolute refractive index. So I believe this is clear. Now let's get to the next point. The next thing we want to really understand is refractive index is not only defined as the ratio of sine I to sine R. That is one definition of refractive index. We have other definitions. Refractive index can also be obtained. Number 2. Number 1 is that refractive index can be obtained from Snell's law, which is the ratio of sine I to sine what? Sine R. That's the first way to obtain refractive index. Let me recap on it. And firstly can be sine I over sine R. This is one way we can obtain refractive index. Number 2 way you can obtain or define refractive index is that refractive index, let me just be using N. So refractive index N is the ratio of speed of light in vacuum, or we can say air, or we can say free space. So it's the ratio of speed of light in vacuum to the speed of light in a material or in a medium, right? So this is another way we can find refractive index. Now the refractive index in this case, since we are considering air, right, to the material, this refractive index is actually what? Absolute refractive index. This absolute refractive, that is the specific refractive index of this material, right? So because that in air is still going to be 1. So what it means is that the refractive index, the absolute, is going to be C, which is speed of light in air, over V, which is speed of light in that particular material medium. So what I want you to note is that refractive index can also be defined in terms of speed of light, and that is the actual origin for the definition of refractive index. Now, another thing we should know is that when light travels from one medium to another medium, the things that can vary for that light is, 1, the speed of that light will change. If it is moving from air into water, when it enters water, the speed will become reduced, the speed will change. Another quantity that will be affected when light travels from one medium to another is the wavelength. The wavelength would change. But then, when the speed and wavelength changes, this changes in speed and wavelength occurs at a constant frequency. So what it means is that when light travels from one medium to another medium, the speed would change, the wavelength would change, or the frequency remains what? The same. The frequency does not change. And this is the simple reason for which you can be in a swimming pool, and then if you have your phone under the swimming pool, you can still browse because the signal will still reach you at the same frequency. If you have your radio, you can still tune to your radio underwater and you still get the signal because the frequency will still be reaching you at the same value. So this is it. Now, if we consider that, you know that C, which is speed, is actually what now? Lambda is actually F lambda, right? So I would say lambda in air all over V in a medium is F, since the frequency is constant, is F lambda in material, right? So if F should fizzle out, then you can get that the absolute refractive index for a material is going to be the wavelength of that material in air over the wavelength of light in air, sorry, over wavelength of light in that material medium. So this is also another relationship for refractive index in terms of speed, in terms of wavelength. So you should note that the frequency remains the same. Then the third way we can define refractive index, number 3. The third way we can define refractive index is in terms of real and apparent depth. So we want to quickly introduce the concept of real and apparent depth. So real and apparent depth. So this is the third way we can define refractive index. What is the idea of real and apparent depth? It's very simple. If I bring a bowl, that contains water, right, and then I bring this my marker, or let's say I bring spoon, and I try to immerse the spoon inside the water. I just hold it so that a part of that spoon is immersed in water. You notice that when you look at that spoon, you notice that the spoon will bend. That is first refraction. And you notice that the spoon appears to be closer to you. It looks as if it's very close to the surface of the water. So that concept is the concept of what? Apparent depth. Now, the same way, if I bring a stone and drop it inside that water, and that stone is at the bottom of that water, and I'm viewing that stone from outside the water, I'm looking at the stone, it looks as if the stone is closer to the surface of that water, right? But not knowing that the stone is actually far deep inside the water. So the situation or the phenomenon for which that stone appears to be closer to you than it actually is what we know as real and what? Apparent depth. So real depth is the actual depth of that stone. The depth from the top to where it actually is what we know as real depth. The apparent depth is what your eyes actually perceive, which is just as a result of what? Refraction. So that is why it looks as if it's close, because when you're viewing it, the light incident from that stone to your eyes, it will bend, it will refract when it's coming out. So it looks like the stone is closer. So that is still the concept of refraction. Let me quickly explain this with a diagram so that we can understand. Now, say we have a pool. We have a pool like this, a pool of water like this. So this is our water like that, right? Now, and then we have a stone. We have a stone at this part of your pool. This is a stone, and you are viewing this stone from the top. This is where you are viewing this from. You're trying to look at this stone. You'd notice that light rays from this stone would be incident, right, to the surface of the water. So this is the incident. If I should draw a number for this, then this is the angle of incident of light from the stone, right? Now, when this comes here, the ray would now do what? It would bend. It would refract to your eyes. So it would refract, right? So that this becomes your angle of refraction. Now, what actually happens here is the ray from the stone is no longer coming straight. It came outside the water and refracted. If you take this, take this straight, you would notice that the stone would now appear to your eyes as if it were at this level, which is no longer the level where the stone is, because of that bending, that refraction. This height from where the stone is to the top to the surface of the water, this height that your eyes is now perceiving, this height is what we know as apparent depth, right? That is what your eyes is perceiving. While this is where the stone is at the bottom. So the height from the bottom to the top of that water is what we know as what now? Real depth. So that is what we know as the real depth. So we can also define refractive index in terms of this concept. And what is refractive index in terms of this concept? Refractive index is actually going to be real depth. I don't have space, please bear with me. It's going to be real depth over apparent depth. So refractive index in terms of this is going to be defined as the real depth, the ratio of the real depth to that of what? Apparent depth. So this is how we can also obtain refractive index. So in these three scenarios, we can always find refractive index. So before I end this video, I would solve one problem so that we can put together all we have learned in this video. So let me get a question so that we can solve. So we have our problem here, and the question says a ray of light is incident on the surface of water at an angle of 30 degrees. Calculate the deviation. So you're incidenting light from air to the surface of water. So this is what we actually have. So this is what we have. So this angle is 30 degrees. This is air to water. So let me call this medium 1 and call this medium 2. So this is N1 and this is N2, right? So now when you do this, you expect it to refract through an angle. And they said a ray of light is incident on the surface of water at an angle of 30 degrees. Calculate the deviation suffered by the ray. So it would, this is the actual part, then this is the amount of deviation suffered. So that is what we want to find. But you can't find the deviation without knowing R. I gave you the formula for finding the deviation. So what we want to do is to first find R using Snell's law. Now, according to what I gave you in Snell's law, we have that, okay, the refractive index N1 is actually equal to 1. That's the refractive index of air. Then N2 is 1.33, refractive index of water. So if we use the concept of Snell's law that I gave, you will notice that N1 sine I equals what? N2 sine R, right? So I have that N1 is what? 1, that's the refractive index of air, times sine 30, the incident angle, equals refractive index of water, which is 1.33, sine what now? R, which is what we're looking for. So if I make sine R the subject, I would have that sine R is going to be 1 times sine 30, all divided by 1.33. So if I punch this, I would quickly get sine 30 is 0.5 divided by 1.33. So I have that sine R is going to give me 0.3759. So this is what I have as sine R. So if I do the sine inverse, I would have that R is going to be the sine inverse of 0.3759. So that when I punch this, I'll get R as 20 degrees, approximately 20 degrees. Now, let's go back because we're trying to find the amount of deviation suffered by this ray. So if you recall, the formula I gave you here is simply delta, which is going to be I minus R. This is the formula I gave you here. Go back and see it. Now we'll have that delta, the deviation suffered, is going to be the incident angle, which is 30 degrees, minus our refracted angle, which is 20 degrees. So our deviation suffered is going to be, okay, sorry, this is 22. This is 22, not 20. So this is 22 degrees. So that when you say 30 minus 22 is going to give us 8 degrees. So this is the deviation. This is the amount of deviation suffered by what? By that light that is traveling. Now I want to stop this video here. In my next video, we'll expand more on the concept of refraction on a plane surface. We'll now look at a rectangular prism. We'll look at what we know as optical invariant. Then we'll consider the total internal reflection and critical angle. Then we'll be done with a plane surface. If you have watched this video up till this point and you are yet to subscribe to my channel, please do well to hit the subscribe button. Subscription is free, and that is the only way you can actually show me your support and let me know that you really value what I am doing. So I believe that what I've explained so far is really clear to you. Thanks for always engaging. Thanks for watching my videos. I do appreciate. Remember, this is Prime Concept. Thank you.